Hi, good morning, everyone. Today we are going to continue our summer school. The first lecture will be given by Professor Enrico Scalas. He will continue to talk about the Monte Carlo simulations of anomalous random walks. Thank you very much, Eric, please.
Thank you very much. So hopefully you will be able to hear me for the whole session. And as usual, I might have occasionally a problem with the audio, and hopefully it's not happening today, but let's see. So I think I can directly start by sharing the screen, but before that, I think yesterday I proposed, and today I will, in the second hour of today, I will present some potential solutions. Of course, there is not the solution because these are programs, and so there are many different ways of obtaining the same result, but still it is useful to see as a feedback what could be done. But let me go straight to the presentation on renewal processes. Yes, to be able to see my screen, and as I was mentioning, the idea is to give you all the details to be able to read this paper that you can see in the background. But now we have seen one element, one building block yesterday, which is the random walk. We have seen, I mean, there are many other questions related to random walks that we did not discuss, but we have seen at least how to find the 1 point probability distribution for the random walk, which is of course not the full characterization of the stochastic process, because to fully characterize the stochastic process you would need all the finite dimensional distribution in their generality, and maybe other specifications on the sample paths. I will come back to this probably tomorrow when we wrap up everything that we have done, but in any case, we have seen, based on some hypotheses, how to get to the point distributions. And these 1 point distributions are very important in applied sciences, because these are the distributions that can help you compare your theory with experiments. But let me now go to the second building block that I was mentioning yesterday afternoon, and namely the renewal processes. Now I will try to put this presentation full screen, which is happening, and structure is pretty much the same as the structure for the other building blocks. So I will give you a definition of renewal processes, one possible definition among several equivalent definitions. Then we will see some properties of renewal processes, and again we will be mainly concerned in the derivation of 1 point probability distributions. And finally, again, I will propose a couple of exercises that are useful, again, if you have time to better understand and grasp the processes. Okay, so what are renewal processes? Now, what you see in this definition 1 is essentially a definition of a random walk, equation 1, but this time for positive random variables. So you have a sequence of independent and identically distributed positive random variables that I denote by JR. Positive random variables is interarrival times between discrete events. So if you have, for instance, an event at instant of time t1 and another event at instant of time t2, the difference t2 minus t1 is the j. Yes, it's distributed according to a common cumulative distribution function that we denote with the same symbol as for the random walk. Then the complementary cumulative distribution function has a nickname in renewal theory, and for renewal processes, it's also known as survivor or survival function. In fact, renewal processes are useful to study also the failure of components. And unfortunately, sometimes, especially in medicine, the components are human beings. And so, for instance, a function like this is used to study the survival of people after the diagnosis of a disease. And this is, for this reason, called survival function. Also, it gives you the fraction of people who are still alive after a certain time after a certain time after the diagnosis, for instance, or after contracting the disease. Then, of course, you can take the first derivative with the caveat that we are assuming that either this first derivative exists of the cumulative distribution function, or if there are jumps in a countable number of points, they can be dealt with as we did yesterday using delta functions. Then again, we define a random walk by summing these independent and identically distributed positive random variables in equation 1. And what is this T, capital T of n, is the instant of the nth event. And again, in renewal theory, these instants also have the name of epochs. And because of the property of the process, of the renewal process, every time you have a renewal, things start from the beginning. So 0 is assumed to be a renewal point. You start from 0, you wait some random time, and then you have another event. And then after this event, things repeat themselves as from time equal to 0. So there is this kind of time homogeneity of the process that is helping in studying its properties. But we are concerned with not only the sequence of events, but also a function, which is a random function. So it's a stochastic process or random process again, counting the number of events between 0 and t. Yeah. So this is neglecting the event at 0 and counting the number of t's between 0 and t. And we use the maximum here because we are assuming that we have a finite number of events. The number is arbitrary, but finite between 0 and small t. Yeah? So you could have 0 events, so nothing happens. You have one event, there is one event in the middle between 0 and t, 2 events, 3 events, etc., but not an infinite number of events. So any finite number. Yes? So we are making this assumption, and in particular, this is true if the density exists as a positive function. So all these objects here are defined for the argument being a positive real variable, and they are the 0 for negative values of the argument u. And in particular, we are interested, as I was mentioning before, in finding the cumulative distribution function for this sum. And also, even more interesting for us is the number, the distribution of the number of events. So this is a continuous random variable, and this is a discrete random variable, and we will see what we can get from the assumptions of independence and identical distribution that we have made for the JI. Before going on, it's a good point to stop a while and see if you have comments or questions related to the definition. I don't see any raised hands. I don't see any questions in the chat. So I will go on sharing the screen. And back to the presentation. Okay, we are now we already solved the problem of finding the distribution of the sum of independent and identically distributed random variables. But there are some peculiarities of positive random variables that are interesting to briefly discuss. So in particular, we know that if you have two positive independent random variables, we consider the sum. The sum is also a positive random variable. And the join, and I'm sorry, not the join, the probability density function of this sum is the convolution of the probability density functions of the two random variables that we are summing. So this is something that we have seen yesterday, and it is valid irrespective of the fact that these are positive random variables. But now you have a positivity condition. So for x smaller than 0, this fx is 0, and this one fy is 0 for x larger than z. So the convolution can be also equivalently written in this way. Yes, so it's as an integral between 0 and z, dx, fx dx, fx of x, and fy of z minus x. So this is the equation that you will often find in the literature for the convolution of positive random variables. It is exactly this one, except for the fact that you have these conditions on the probability density functions. They are 0 for negative argument. And so if you are integrating over something which is 0 here, you get 0. So the only non-zero contributions to these integrals are between 0 and z. That's nice. So and we have also another interesting difference, small difference. The characteristic function that we have defined yesterday for a random variable is the Fourier transform of the probability density function. And for positive random variables, it is more useful to use another transform, the Laplace transform, which is the exponential and then the expected value of the exponential of minus sx. And the Laplace transform is the integral from 0 and infinity of the function multiplied by this kernel exponential of minus sx. So this is the expectation of this random variable here. And then you could try and it is a very simple exercise because it only involves integrals over elementary functions for the exponential distribution where the density is exponential of minus lambda x. And if you do so, you find that the Laplace transform of the density is a lambda over s plus lambda, and the Laplace transform of the survivor function is 1 over s plus lambda. Yeah, the survivor function is the exponential of minus lambda x. So it does not have this lambda in front, but the integral is exactly the same. And you can try as an exercise to make these calculations, and this is some result, and then we will see now why this is useful. Now, we have seen that if you consider the sum of two independent random variables, the characteristic function is the product of the characteristic function of the random variables. Similarly, given the properties of the exponential function, you get the same for the Laplace transform. So in the end, the Laplace transform of this convolution, 3, will be given by 5. So the product of the Laplace transforms of the two summands. So let us follow the derivation. So you write it explicitly what the Laplace transform is. Then you replace z with x plus y. Then you notice that the exponential of minus s x plus y is the exponential of minus sx multiplied by the exponential of minus sy. And then you have to take this expected value. Now the two random variables are independent. Functions of these random variables are also independent, so you can use independence. And if you have independence, you factorize the joint probability density function, or you factorize the distributions or the measures if you prefer, and therefore the expectation of the product becomes the product of the expectations. This is not true in general. So you need independence for this, and then you get your result. And so very easily, we can use this result to compute the Laplace transform of the density of Tn. Remember, Tn is the sum of n independent and identically distributed random variables. Here it is. So, using this formula 5, you find immediately that okay, let us apply this result of the Laplace transform of the exponential distribution to get this Laplace transform here, lambda to the power of n divided s plus lambda to the power of n. And this is Laplace transforms that you can invert analytically by using the inversion formula for the Laplace transform, or you use more easily a table of Laplace transforms. You go in the table, look for this function here, and you will find that the inverse is this one. And this distribution has the name of Erlang distribution with this probability density function here. This is, again, everything is here defined for positive u, and negative, and for negative u, everything is 0. Okay, so now you see that in 2 steps you get this result here. You can also do it directly by using the convolution formula. For the exponentials, it is very easy to use the convolution formula. But for more complicated functions, it may not be so easy to make n-fold convolutions, and therefore the algorithm here that we have used with the Laplace transform is much easier to use in the general case. Okay, I will stop sharing because I can see, Jack, you are right that the Erlang distribution is an example of a gamma distribution and as a sum of exponentials. There is a theorem to gamma distributions that can be proved using this method that we have seen on Laplace transforms, or can be used, or can be proven directly, that the sum of gamma distributions with certain parameters is still a gamma, where one of the two parameters, which is the scale parameter, you sum it and you get still a gamma. Yes. Because the exponential is an example of a gamma distribution, if you sum several gammas, you get the Erlang distribution, so it is true that many of you might have already seen this result in another context or proven in a different way. And now we have the distribution of. Let us try to compute the distribution of the counting process. Again, in some generality. You can again use the method of Laplace transforms to get the Laplace transform of the probability that we call PNT, which is the probability that you have n events between 0 and t. Now, you can convince yourself that the event that nt is equal to n is the same as the event that Tn is smaller or equal than t. So there are n events up to t, and the next event will occur after t. So the probability of nt, this function will, oh, sorry, here there is a typo. This should be the same symbol as here. I will correct it later. Let's see if I put this typo somewhere else. I don't think so. No. Okay. Yes, so this is the symbol here. In any case, it is clear this is a probability of nt equal to n. And then I have not put here the set symbol with the curly brackets, but it should be there. We don't use it in probability because it is cumbersome, but this always the probability is the probability of an event. So the event can be represented either by a proposition or by a set. And in this case, it is, I mean, the two representations are really equivalent, even if this is quite deep. And this set here is equivalent to this set. So they are equal sets. So I put this here. Maybe I should have put another curly bracket here, but it is clear what I'm trying to do. And now here, I am just interested in letting Jn plus 1 appear, because Jn plus 1 is independent on the past. And Tn plus 1 is Tn plus Jn plus 1. And so this event here is equivalent to this event here. And now I am using another trick. And namely that the probability of a set is equal to the expected value of the indicator function of the set. This is easier to understand that this probability is given by this integral, which is exactly the expected value of the indicator function of the set, where I have already used the fact that Tn and J are Jn plus 1 are independent. And I have also used the fact that Jn plus 1 has the same distribution as J1. So this expected value is given by this formula here, which gives you this one here, number 6. So it's a convolution between Ftn and the cumulative, the survivor function computed in t minus 1. T minus u. Now you remember that the Laplace transform of the convolution is the product of the Laplace transforms. So you take the Laplace transforms here and here, you get this equation here. So here you have the Laplace transform of the density of Tn, and here you have the Laplace transform of the survivor function for J1. And this we computed before is the nth power of the Laplace transform of the density of J1. And then you have equation 7, which gives you the Laplace transform of the counting process distribution, the 1-point probability distribution for the counting process. Equation 7 is in fact my first entry point in renewal theory. Back in 2003, I was not yet in probability, but in particle physics. So I was at CERN in Geneva, and I was thinking about the generalization of the exponential distribution to get to some fractional calculus equations. And then I found this kind of derivation in an encyclopedia, in an article written by some physicist working at the Office for Naval Research and in the United States. Yes, from here, I introduced a renewal process together with my co-authors Mainabi and Gorenflo of Mittag-Leffler type that we will briefly discuss later. I would like to also mention that it is very easy to see that the probability of NT being 0 is just the survivor function. This is a remark. And it is a good point to stop sharing and ask if you have comments or questions about this derivation. I would like to mention that with this derivation, you get an algorithm to compute the 1-point probability distribution for your counting process. If you know the Laplace transforms of the density of the inter-arrival times and of the survival function for inter-arrival times, you have immediately the Laplace transform of the counting process. Good. So I will share the screen again later on and comment the question. And let us apply these results in the exponential case. Remember, we computed these two Laplace transforms, which are appearing here. And if I use these two results, I get this nice Laplace transform for the counting process when the inter-arrival times are exponentially distributed. Lambda to the power of n, and then divided by s plus lambda n plus 1. Again, this is one of those Laplace transforms that you can find in tables of Laplace transforms, and if you invert, you get the formula for the Poisson process. It turns out that for any t, the counting process has a Poisson distribution of parameter lambda t. So Pnt is nothing else than lambda t to the power of n divided by n factorial exponential of minus lambda t. In other words, the Poisson process is the counting process for the renewal process where the inter-arrival times are exponentially distributed with parameter lambda. Now, of course, this is not yet the proof that this is the Poisson process. We would have to show that the increments of this process are independent. Remember, the Poisson process is a Lévy process, so it has this distribution, but also you need to show that the increments are independent. We are not showing here that the increments are independent. It's not very difficult to make it, but to prove this. But I mean, it's an unnecessary complication for our discussion, where I'm giving you the elements to understand that particular thing. And now, in this case, the probability of not having events up to time t is just the survivor function for the exponential distributed random variable. So it's the exponential of minus lambda t. And of course, you can compute, now that you have the distributions, many quantities, including the expectation of the counting process. So what is the expected value of nt? Well, we already know, for instance, for the Poisson process, what would be the expectation. But let us see what we can do. So if I make the Laplace transform of the renewal function, which is the expectation of n of t, I get this relationship here where by convergence I can really put the integral within the series. And then I make the transformation, the replacement that we have seen before. So I can put this out, and I put also one of the fj's out, so that I get the sum for positive, for n larger or equal than 1, n equal to 0 gives a 0 contribution here of this quantity here, and this is the derivative of a geometric series. So you get to equation 8. It is a good exercise for you to justify all these equalities in terms of what you know about convergent series. Now, remember that the cumulative distribution function is the derivative of the density, and the complementary cumulative distribution function is 1 minus the cumulative distribution function. So all these Laplace transforms are not independent, and in fact, you have relationships between them, and you can use relationships between a Laplace transform and its derivative when you have to assume also something about the initial values. I am not proving this in detail in order to save some time, but it is not very difficult to derive these relationships here. And so equation 8 becomes equation 9. After these changes of variables, where this is the Laplace transform of the cumulative distribution function for the inter-arrival times. And here you have the density. So you see, you can express again the expected value of the renewal process, counting process, in terms of the distribution of the inter-arrival times. And if you invert this equation, you multiply everything by 1 minus small f tilde j 1 of s, get this integral equation, which is this so-called renewal equation for the renewal function, equation 10. Very well. What happens here in equation 9 if we apply it in the exponential Poisson case? We get this Laplace transform here. When you invert, you get, in fact, that the expectation of nt is what we would have expected from the fact that it is Poisson distributed with the parameter lambda t, namely ht is equal to lambda t. This remark immediately leads also to derive the variance of the counting process, which is the variance of Poisson random variable of parameter lambda t, which is equal to the expectation. And now let us come to the exercises. So choose your favorite independent and identically distributed sequence and write a Monte Carlo program to estimate the counting probability. So the probability of having 0 events, 1 event, 2 events, etc. You have to run the simulation of the counting process up to a certain time t many times. And then you make a histogram of the values of the number of events that you find between 0 and t. And then you can compare the Monte Carlo results with the theoretical values of p and t. You can try your code using the Poisson process. We have yesterday already written a program that is simulating the Poisson process, so you might use that particular code. And the second exercise is on the moment generating. What is the moment generating function? If it exists, is the exponential, is the expected value of the exponential of z and t. So it is this sum here. And the exercise is to prove that the moment generating function for the Poisson process has this shape. Once you have the moment generating function for a counting process, you can, by taking derivatives with respect to z, find all the moments of the counting process. And you can derive the results that we have seen before from this function here. Okay, so this is what I wanted to tell you about a renewal process. And because we have 10 minutes, before I stop sharing for a second to see if you have comments or questions about renewal processes. Again, I have omitted a lot of results on renewal processes, their stability, the renewal theorem, etc., etc., etc. But all these results are available in standard probability textbooks and in chapters related to renewal processes. Renewal processes are quite important in many areas of applied probability. The theory of reliability already mentioned the application in for components of a device. Typical examples are bulbs. It gives you an idea on it is useful to estimate the probability of the failure of a component, and then maybe the failure of itself. It is also used in queuing theory because the assumption for queues is sometimes, actually, the easiest assumption is to have a queue coming with customers that coming with Poisson process and are served with exponential time. So this is the MM1 queue where M is Markovian, and I did not mention, in fact, another important property of the Poisson process. It is the only renewal process that is also Markovian due to the independence of the increments. You can prove the Markov property for the Poisson process. Good. So I don't see a major questions here in the chat, so I will share the screen again. And on the screen, you should be now see a program that I call the digital die, where I am presenting maybe 3 possible simulations of a die. Let's start with what I call here case 3. Which I call brute force simulation, and this is the one I was somehow proposing to you. Now here, what I'm doing is I am creating a slightly biased die, where if I am not wrong here, the probability is summing up to 1, but each phase has a probability slightly different from 1/6. Let us try and see what we get with these 3 first lines. Shape, and the sum of P, if I am not wrong, should be 1. Yes. Now, what do you see here is the number of samples, which is 100,000 in this case, and then the assignment of a perturbation epsilon of the probability, which is 1/100. And then the target probability distribution, which gives probability slightly smaller than 1/6 to the outcome 1, slightly higher to the outcome 2, etc. Now, to get the cumulative distribution function, you just consider the cumulative sum of P. Then you generate 100,000 uniform random numbers, and you introduce a variable die cast in which you put zeros. Notice this syntax, which is peculiar of R, where you have to use this function C to create an array or a vector. So this is adding elements and creating an array. Yes, so if in fact, P is a one-dimensional array with these 6 elements. And now that I have the cumulative distribution function, I can start making transformation using this nice function, which is finding for me the index of the vector u, where the condition that u is smaller than the first value of the cumulative distribution function. And then once I have these indices, I put here the result 1 in those values. Remember that this was a repetition. So this function rep is repeating values of zeros 100,000 times. So here we will have a certain number of ones. Then if the probability, if the uniform distribution u is between the first and the second value of the cumulative distribution function, you get 2. If it is between the second and the third, you get 3. If it is between the third and the fourth, you get 4. If it is between the fourth and the fifth, you get 5. And if it is between the fifth and the sixth, you get 6. And here you are using the logical ampersand sign, which means and. And so this is the intersection of these 2 conditions always, and it is finding for you the indices in which this is satisfied. So this which comment, which is equivalent to the find command in Octave or MATLAB, it's very handy to do these simulations. And now I define a vector of frequencies, and again using which I look at the values, at the number of instances in which you have 1, 2, 3, 4, 5, 6 with a 4 cycle, which has this syntax in R, and then divide by the total number of instances in order to get the frequencies, and then I can compare frequencies with the theoretical probability. Let's do this. So I think I run up to here, so I start up to here. Let's see. And you see, this is the theoretical probabilities that we have defined, and these are the Monte Carlo estimates of this biased die, and you see that the match is reasonably good. Actually, I would say quite good compared to the theoretical value. We have still 1 minute just to mention that you can also plot and go back to the console here. The frequencies. And now you see that I have to remember what is the theory and what is the Monte Carlo simulation. So the theory is these vertical lines, and the circles are the Monte Carlo simulation. And you see that there is a very nice match between the theory and the Monte Carlo simulation. I don't know if your simulation of the die was like this one, or you use a different method. There are many other ways of simulating the die. And in this program that I will give you later, there is a possibility of using the sample function. And you can use the sample function using uniform distribution, but also biased distribution. So it gives you immediately a simulation of a coin, die, or whatever you want when you have a finite number of possible outcomes. Okay, I will stop sharing now, and I am now waiting for questions.
So Erica, you finished this morning's session, is right?
Yes, that's right. If there are no questions, it's finished.
Okay, let's see if there's any questions. And I stop recording. Okay, so yeah, that's yeah.
Thank you very much for your attention, and yeah.